Hello all, welcome to this video on theory of computation. Today I'll be talking about some central ideas of theory of computing. Theory of computation is the theory of what can be computed and what cannot be by real-world computers. It develops formal mathematical models of computation that reflect real-world computers. So the following presentation majorly have these four sections, which are formal language theory, automata theory, computability theory, and complexity theory. Formal languages are precisely defined set of strings formed from finite alphabet based on a set of rules or grammar. There are regular languages, context-free languages, context-sensitive languages, recursive languages, and recursively enumerable languages. The general idea of a hierarchy of grammars was first described by Noam Chomsky in his Three Models for the Descriptive of Language during the formalization of transformational generative grammar that posited transformation rules that mapped a sentence's deep structure to its pronounced form. He theorized that four different classes of formal grammars existed that could generate increasingly complex languages. Each class can also be completely generating the language of all its inferior classes. Now there is finite automata, push-down automata, linear bounded automata, and Turing machine. Automata theory deals with the study of abstract machines and the problems they can solve. So they classify automata by the class of formal languages that these automata can recognize. Grammars generate languages which are recognized or accepted by the automata or the machines. Computability theory talks about the fundamental capabilities and limitations of computers. They classify problems as solvable and unsolvable. There are some formal models of computation, like the Turing machine, which is the ultimate computer. This is a theoretical machine with infinite tape or memory, read or write head like the CPU, and a set of rules like a program. Then there is recursive functions, which is a math-based computation, also a mathematical way to define computation using functions. Then there is lambda calculus, which is the foundation of functional programming, that is a symbolic way to represent computation using functions only. And finally, the production systems, which includes the Post and Markov algorithms, which is a rule-based computation similar to the grammar rules in programming languages. In computability hierarchy, there are decidable languages, which are also called solvable languages, computable languages, recursive languages, and Turing decidable languages. So, a decidable language is a formal way of saying that we can write an algorithm or a Turing machine that always correctly answers yes or no for any input in the language. Then there is the Turing undecidable language. So, this is a problem where no algorithm exists that can always give a correct yes or no answer for every possible input. An example would be a halting problem. So, can we write a program to check if another program will run forever or stop? Then there is semi-decidable language, or it's also known as recursively enumerable language or partially decidable language or Turing recognizable language. Here, if the input is in the language, then the Turing machine will halt and accept. If the input is not in the language, then the Turing machine may run forever. Then we have the Turing unrecognizable languages. No Turing machine can even list all the valid answers, unlike recursively enumerable languages, which is worse than undecidable and also not even partially solvable. Complexity theory looks into what makes some problems computationally hard and others easy. It can be measured using complexity, which can be either time or space. It also tends to classify solvable problems according to their degree of difficulty as easy ones and hard ones. There comes the concept of intractability theory, which refers to problems that are theoretically solvable but practically impossible due to the excessive time or memory requirements, even for powerful computers. Now, looking into the complexity hierarchy, we have P problems which are solvable quickly in polynomial time by computers like sorting a playlist alphabetically, which can be fast even for thousands of songs. The NP problems, where solutions can be verified quickly but not necessarily found quickly, like solving a jigsaw puzzle, which is hard to assemble but easy to check if it's correct. Then there is P space problems, which are problems solvable with limited memory but possibly long time, like solving a maze by retracing steps. You don't need extra tools, just some patience. Then there is exponential time problems requiring exponential time, which becomes impractical for large inputs like trying every possible combination of a 100-digit lock, which is doable but very slow. Now we look into the motivation for studying computability. The first one would be to understand the problem's solvability. Computability theory determines which problems can be solved by algorithms. There are decidable problems for which an algorithm exists, and there are undecidable problems for which no algorithm can solve them for all the cases. An example would be the halting problem. The second reason would be to know the limitations of computation, which will establish a boundary on what can be computed. There is the Church Turing thesis, where any computation function can be computed by a Turing machine. Then there are non computable functions like the busy beaver problem, which takes maximum steps a Turing machine can take before halting. These guide algorithm design by identifying impossible tasks. Now we'll look into the need for mathematical modeling in automata. First would be for formalizing computation. There are abstract models for computational processes like a finite automata where systems are modeled with limited memory, and Turing machines which will model general purpose computation. So this will enable precise analysis of computational behavior. Another reason would be the predictable behavior and verification, which ensures that the systems behave as intended, which will involve model checking, which will verify if a system meets the specifications, and state transition diagrams, which will visually represent the state behavior. An example would be a protocol verification, which will ensure the network protocols avoid deadlocks. And finally, the hierarchy of computational power. It classifies automata based on computational capability. So these key models will help select the right model for a problem. Now we'll look into automata through some simple models. The first one would be a coffee vending machine, which is a finite state machine that moves between different states based on the user input. So the states here will be what the machine can be doing. First one, to be in the idle state means it is waiting for the user to insert the coin. Then there is a coin inserted state, which means the user has paid for the coffee. And then there is the option selected phase, which means the user has chosen the coffee. Inputs are what makes the change of state. So when the user inserts a coin, means the money is added. Then there is the select option, which will be to choose the coffee. And then there is the dispensing part, which will be to offer the coffee to the user. Then there are transition, that is the rules for changing state. So from idle state, If the coin is inserted, it moves to the coin inserted state. From there, if we select the drink, then the control is moved to the option selected state. Then if the coffee is dispensed, then the system moves back to the idle state. Now, why this can be called as a finite state machine? Because it has fixed number of steps. It reacts to user inputs by changing the states. It also follows strict rules. For example, the coffee cannot be dispensed unless the user pays the amount. Now, finite automaton are a useful model for many important kinds of hardware and software. For example, software for designing and checking the behavior of digital circuits. Another example is a lexical analyzer of a typical compiler. That is the compiler component that breaks the input text into logical units such as identifiers, keys, and punctuation. Also, in software for scanning large bodies of text, such as collections of web pages, to find occurrence of words, phrases, or other patterns. Software for verifying systems of all types that have a finite number of distinct states, such as communication protocols or protocols for secure exchange of information. There are many systems or components, such as those listed now, that may be viewed as being at all times in one of the finite number of states. The purpose of a state is to remember the relevant portion of the system's history. Since there are only a finite number of states, the entire history generally cannot be remembered. So the system must be designed carefully to remember what is important and forget what is not. The advantage of having only a finite number of states is that we can implement the system with a fixed set of resources. For example, we could implement it in a hardware as a circuit or as a simple form of program that can make decisions looking only at a limited amount of data or using the position in the code itself to make the decision. Now we can look into a simpler example, which is a simple on-off switch. The device remembers whether it is in the on state or the off state, and it allows the user to press a button whose effect is different depending on the state of the switch. That is, if the switch is in the off state, then pressing the button changes it into the on state, and if the switch is in the on state, then pressing the same button turns it to the off state. As for all finite automata, the states here are represented as on and off. The arcs are labeled as inputs that represent the external influence on the system. Here, both of them would be push, which represents user pushing the button. The intent of the two arcs is whichever state the system is in, when the push input is given, it goes to the other state. Here, one of the states is designated as the start state, where the system is placed initially. Here, we take it as off. So, it is often necessary to indicate one or more states as final or accepting. Entering one of these states after a sequence of input will indicate that the input sequence is good in some way. For example, here we can take the state on as accepting because in that state the device being controlled by the switch will operate. It is conventional to designate accepting states by a double circle, though we haven't made any such designation here. Sometimes what is remembered by a state can be much more complex than a simple on-off choice. Now this shows another finite automaton that could be part of a lexical analyzer. The job of this automaton is to recognize the keyword then. It thus needs 5 states, each of which represent a different position in the word then that has been reached so far. These positions correspond to the prefixes of the word, ranging from the empty string to the complete word. So here 5 states are named by the prefix of then seen so far. Inputs correspond to the letters. We may imagine that the lexical analyzer examines one character of the program that is compiling at a time, and the next character to be examined is the input to the automaton. The start state corresponds to the empty string, and each state has a transition on the next letter of then to the state that corresponds to the next larger prefix. The state named then is entered when the input has spelled the word then. Since it is the job of this automaton to recognize when then has been seen, we could consider the state the non accepting state. Now we'll look into some simple problems related to automaton theory. The first one is to have the alphabets that is required to generate a language for all valid decimal numbers. So decimal numbers will include numbers from 0 to 9. Also, since it's a decimal number, we'll include the symbol dot. So the language will include all these numbers along with the dot. Now the second one is the rule of the language is given. We are to generate the string based on this rule. So it means the language will have at least two A, which will have two alphabets A and B. So we have to list all the strings in the language which has at least two A and also which has a length of 3. So we'll take the case where there are two A's and one B. So we'll have AAB, ABA and BAA. Then we take the case where we have three A's, just AAA. So the length is 3. So these four will be the list of strings that are present in this language L. Now the third question is whether the language L equal to the empty string and L containing 5 the same. So L containing the empty string means though the string is empty, that's counted as a string there. But when it comes to 5, it means there are no strings present in that language. So both of them would mean different. We look at another problem where we are given the grammar and we have to generate the language with different values for n. So the language contains a raised to n, b raised to n. Now we give for n is equal to 0, we'll get s giving lambda. So when n is 1, we have s giving ASB. So we give next substitution as lambda because n is 1, then the language we'll get is AB. So it's AB. Then when n is 2, we'll substitute s with s ASB. We'll do a second substitution with the same combination which is again ASB. So we'll get AASBB. We'll do the substitution again. But that's not required here because the value of n is 2. If there is n is equal to 3, we can go on like that till the value of n ends. So we'll stop here by giving the substitution of lambda instead of s. So the string will be AABB. And the last question is, we are given a grammar and we have to check whether a particular string is present in it. Same way we'll do substitution beginning with s giving 0 as 1. We'll try one more substitution which will have this s being replaced by 0 as 1. So it will give 0 0 as 1 1. We'll do it again because the required string contains 3 zeros and 3 ones. So substituting this here, we'll get 0 0 0 s 1 1 1. Since we only need to do it thrice, we'll replace s with lambda. So this is the string we got. So that is the same as the one we had to check. So that will match when the value is n equal to 3. That's all for now. Thank you for watching.